Welcome everyone, I'm Norman Wahlberger. This is part of a course on algebraic topology. And in my last lecture at UNSW, my camera's microphone wasn't working properly, so I'm repeating the lecture. And it was on commutative groups. We were talking about some additional aspects of commutative groups. Now this is just an introduction to the basics of the subject, and it is not a comprehensive treatment. I'm just reviewing and summarizing the main things. So we ended up with the last lecture mentioning this important theorem, the structure theorem for finite commutative groups. So every finite commutative group is isomorphic to a direct sum of cyclic groups. And this might be a good place to mention that the word commutative and the word abelian mean pretty well exactly the same thing. Abelian is named after Niels Abel, who was a very important Norwegian mathematician, one of the pioneers of group theory. And here is what the theorem states in terms of writing it down. So if we have a general group G, then this is our symbol for isomorphism, which more or less means equal to. So G is isomorphic to, and here's a direct sum of cyclic groups. Zn1 plus Zn2 plus all the way up to some Zn sub k. And these numbers n sub 1, n sub 2 up to n sub k can be arbitrary positive natural numbers. 1, 2, 3, 4, 5, and so on. And I remind you that this direct sum means that we're considering objects which are k-tuples. In other words, they're like vectors with k components. The first component, A1, has to be an element of Zn1. The second one, A2, is an element of this one here, up to the kth one, which is an element of this one here. And let me remind you that Zn1, for example, can be thought of as just the natural numbers, including 0, and then 1, 2, 3, all the way up to n1 minus 1. So Z5, for example, is the set 0, 1, 2, 3, and 4, with altogether 5 elements. So the direct sum consists of this kind of object, and we add two of them just by doing the addition component-wise. So we add the two guys in the first place by working in this group, we add the two guys in the second place by working in this group, and so on. It's useful to point out that the size of this group on the right-hand side is just the product of the numbers n1, n2 up to nk. Because there are n1 choices for a1, n2 choices for a2, up to nk choices for n sub k. All right, we're not going to prove this theorem or anything, it's a major result, but we do need to say what exactly this isomorphism means. What does this symbol, which is our representation of equality in the group theoretical context, what does that actually mean? So this is a situation that we face repeatedly in abstract algebra. Once we've defined a particular type of mathematical object, particular type of algebraic mathematical object, say, it's usually important for us to say when two such objects are going to be considered equal. There's many situations where two objects are almost the same except they're labeled differently. We don't want the difference of labels or names to interfere with our saying that those two objects are really essentially the same. So the notion of isomorphism captures this very important aspect of algebraic theory. So for groups, here's the definition, that groups G and H are isomorphic, and we write it this way, G with a sort of an equal sign with a little wavy tilde on the top. G is isomorphic to H precisely when we can find a bijection, say phi, from G to H, satisfying these three conditions. Let me remind you that a bijection means a correspondence which is one-to-one and onto. It means that this phi is a complete pairing up between the elements of G and the elements of H. So for every element in G, phi gives us a corresponding element of H in such a way that the two collections, G and H, are completely matched up. Okay, so that bijection has to satisfy a few additional properties because we want it to respect the algebraic structure that we've got, namely the group structure. So the important ingredients in the group structure are, well, the simplest thing I suppose is the identity. So we want this bijection to make the identity in G correspond to the identity in H. This E sub G refers to the identity element in G. This is the identity element in H, and we certainly want those to be paired up. The next thing that we have, of course, is the multiplication itself. And I'll just write star here. But what this here is G1 star G2. It refers to two elements in G, and this is the product of those two elements in G. And we're saying that if we take the image of that product, then what we get is the product of the images. So if we look at where G1 goes and where G2 goes, it goes to 5G1 and 5G2. These are two elements in H. When we multiply them, we should get phi of G1 times G2. So I'm not making it explicit here, but it's important to be aware that this multiplication here refers to the multiplication in G, while this multiplication refers to the multiplication in H. And finally, it's natural to require that this map phi preserve our notion of inverse, namely that phi of G inverse equals phi of G, all of that inverse. So if we have an element G in the group and we have its inverse in G, then those two elements end up being inverse elements in H. Now often all of these things are not written down, but I think it's reasonable to write all of them down, even though they may not be necessary, because this makes it clear that this bijection has to respect all of the structure that we've built into the group. Now for commutative groups, which we're talking about mostly today, we generally write the multiplication or operation additively with a plus sign. In that case, we can rewrite these conditions more in line with the notation for commutative groups. So the identity in G is the 0 in G, so we require the 0 in G to go to the 0 in H. Then the operation is addition, so the second requirement becomes this one. And the inverse operation becomes what we write as a negative. So phi of minus G is minus phi of G. So let's have a look at an example. Here are three groups of order 4, that in other words have 4 elements altogether. There's the cyclic group Z4. There's the direct sum Z2 plus Z2, consisting of pairs of elements, each component belonging to Z2. Z2 only consists of 0 and 1. And here's the Klein 4 group that we saw in terms of symmetries of a square. Now, according to the structure theorem of finite commutative groups, this Klein 4 group ought to be isomorphic to one of these two, because these are the only sums of cyclic groups whose total order is 4. So which is the correct isomorphism? Well, if you look at the table and sort of see the pattern, you see that it's these two that are isomorphic. One way of seeing that, for example, is the identity. The identity is appearing here down the diagonal, telling us that any element times itself is the identity. So in other words, any element squared in this group is the identity. Here we see the same kind of thing here. 1, 0 plus 1, 0 is 0, 0. And I remind you that's because 1 plus 1 is 0 when we're working mod 2. So we see the identity is down here. That's the same pattern as up here. And so indeed the Klein 4 group is isomorphic to Z2 plus Z2. And to make that official, to exhibit that isomorphism, we would like an actual isomorphism. Here is such an isomorphism. It's not the only one. So it's a mapping from the 4 elements in K to the 4 elements in Z2 plus Z2. 1 is sent to 0, 0, A is sent to 1, 0, B is sent to 0, 1, and C is sent to 1, 1. And you can check that, well, this makes a correspondence between these two tables. In other words, the two tables are really essentially the same up to relabeling. And this is a way of relabeling the tables to go from this one to this one. So the groups are isomorphic. Sometimes it's useful to observe that groups are not isomorphic. For example, Z4 is not isomorphic to Z2 plus Z2. One reason we've already mentioned, because in this group, every element square is the identity. But in this group, that's not the case. Another common way of checking whether groups might not be isomorphic is to look at the order of elements. Z4 contains an element of order 4, but Z2 plus Z2 does not. So let me remind you what the definition of the order of an element. If you have a group G with multiplication star, then the order of an element little g in that group is the least positive integer n satisfying g times g times g all the way up to g, n times is the identity. So it's the smallest numbers of g's that you have to multiply together to get the identity. And we write order of g equals n. And it's important to mention that sometimes elements in a group don't have to have such a finite order. For example, if we're working in Z, the element 1, or in fact any element, does not have a finite order. You can add 1 to itself as many times as you want, you're never going to get 0. Sometimes we say that 1 has infinite order in that case. So in Z4, for example, the order of 0, the identity element, is 1. The order of 1 and the order of 3 are both 4. 1 plus 1 plus 1 plus 1 is 0 in Z4, and 3 plus 3 plus 3 plus 3 is also 0 in Z4. But no smaller number works. However, for the element 2, its order is only 2, because 2 plus 2 is 0 in the group. So you only need 2 2's added together to get 0, while you need 4 1's or 4 3's. These two have order 4, this one has order 2. However, in Z2 plus Z2, well, the order of the identity is still 1, but the order of the other 3 elements are all 2. So you can tell by looking at the orders of the elements that these two groups are not isomorphic. So while we're talking about isomorphisms, let's briefly mention automorphisms. These are isomorphisms from a group to itself. So a function from a group to itself is an automorphism if it's an isomorphism of groups. In other words, if it satisfies the 3 basic properties of an isomorphism. The identity mapping, which just takes every element to itself, is always an automorphism, automatically. But there can be other automorphisms too. For example, if we look at the Klein 4 group, then we saw that in the multiplication table, the 3 elements A, B, and C pretty well played a symmetrical role. They were pretty well indistinguishable. A times B equals C, B times C equals A times C equals B. So that means that every permutation of A, B, C is an automorphism, or gives rise to an automorphism, because of course you still have to send 1 to 1. So the automorphisms of K themselves form a group. In fact, the symmetric group on 3 letters. That's the non-commutative group, so it's a little bit outside of what we've been talking about so far. So as an exercise, you might like to show that automorphisms of G is a possibly non-commutative group for any group G. This is another interesting way of getting new groups from old groups, is to take a group G and ask what are all its automorphisms. That's a new group. And for fun, you might like to explicitly look at the automorphisms of Zn, say for n equals 6, 7, or 8. And maybe from that you can figure out what the automorphisms of Zn look like for any integer, positive integer n. The notion of an isomorphism between groups is a very rigid and strong one. And in group theory, it's important to consider things which are pretty close to being isomorphisms, but which are not quite as structured as isomorphisms. They're called homomorphisms. And they concern relations between two groups as well, but the relation doesn't have to necessarily be a bijective one. So the definition is that a homomorphism, phi, from a group G to a group H, is a map which does not necessarily have to be one-to-one, or doesn't have to be onto, just any old map, which still satisfies the 3 conditions that an isomorphism satisfied. Namely, it sends the identity in G to the identity in H. It preserves or respects multiplication, the multiplication in G, the multiplication in H, and it sends inverses to inverses. So if a homomorphism is also a bijection, then it's an isomorphism. But it's possible for a homomorphism to be neither one-to-one nor onto. Because of that, it then becomes interesting to consider, well, if it's not onto, well, what is the image? And if it's not one-to-one, then sort of how do we measure that non-one-to-oneness? And there are then these 2 important notions that go along with homomorphism. So given a homomorphism from G to H, we can define the image of phi. And that's those H in H, the elements in the second group, which are actually hit by something in the first group. So just the image of the function in the usual sense. While the kernel of phi consists of those types G in G, those elements G in G, that have the property that they get sent to the identity in H. So certainly we know that the identity in G has this property, but there very well might be other elements in G that get sent to this single special element in H. That's called the kernel of the homomorphism. All right, and then a very important exercise that you should do, if you haven't done this at some point, is to convince yourself that the image of phi is a subgroup of H. And generally we write this for being a subgroup. So image of phi, this less than means that this is a subgroup of that. And that the kernel of phi is a subgroup of G, written like this. In fact, in general, the kernel of phi has some extra property that makes it even more important. All right, so we have this notion, a general notion of homomorphism that allows us to relate 2 different groups. And associated to such a homomorphism are these 2 reasonably natural subgroups of the 2 groups, the image of the homomorphism in H, the kernel of the homomorphism in G. All right, now let's talk about a somewhat more advanced concept, the idea of cosets of a subgroup, and then this additional notion of a quotient group. So the idea of dividing one group by another. This is often a concept that causes students some difficulty, and one of the reasons is that if you do it in the non-commutative situation, it's more complicated and a little bit harder to understand than in the commutative one. So it's best to understand this first in the commutative situation, which is what we're going to do. All right, so we're going to stick with an example here, the example of the integer z. And let's visually picture these integers along a number line, going off in that direction and in that direction. 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, and so on. So just the additive group of integers. And let's consider a subgroup of the integers. And the subgroup that we're going to choose is the subgroup 3z. We're going to call that h. So 3z just means all the multiples of 3. 0, 3, 6, 9, as well as the negative ones, minus 3, minus 6, and so on. All multiples of 3. That is a subgroup because it contains the identity, and it contains the sum of any two elements. So 3 plus 6, the sum is 9. It's also in the subgroup. And it contains the negative, the inverse of any one of its elements. 6 is in the subgroup, so is minus 6. Okay, so we have this situation. We have the big group G, the subgroup H. We're now going to look at some additional objects that are very closely associated to the subgroup H inside G. These are called cosets of H. And for this group, there are, well, 3 cosets. One of them is H itself, and then there are 2 other cosets, which we might call 1 plus H and 2 plus H. So what are these? Well, 1 plus H is what you get when you just take the coset H, or the subgroup H, and you add 1 to all of its elements. Essentially translating the whole thing over by 1. So we take the red points, we move them all over by 1, we get the green squares. There, 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 there. Also spaced equally 3 apart, containing 1, 4, 7, minus 2, minus 5, and so on. Arithmetically, these are just the numbers which are congruent to 1 mod 3. So let's denote by 1 plus H that object, that type of number. Similarly, we might shift once more by another 1. In other words, shifting the original subgroup by 2 to the right, say. We'll call that 2 plus H, and here it is in the blue triangles. So 2, 5, 8, along with minus 1, minus 4, and so on. Of course, we can do other things. We could also shift by 5 or by minus 12. But any further shifts are not going to give us any new structures. We're always going to get one of these guys. So for example, if we shifted 1 to the left, or minus 1 plus H, well, that would be the same as this 2 plus H. So there are really only 3 cosets, and you can see that they subdivide or partition the group. This is a very important point, that cosets do not overlap. Well, unless they're the same, like 2 plus H is the same as minus 1 plus H. But otherwise, they do not overlap. They're distinct, and every element is in some coset, because you can always translate so that the given element is part of the translation. Now, what makes these cosets interesting is that the cosets themselves have an algebraic structure. Because H is a subgroup, let's have a look at that. So here's the algebraic structure of these 3 cosets. H, 1 plus H, 2 plus H. H, 1 plus H, 2 plus H. I'm adding them. I'm claiming that 1 plus H plus 1 plus H is actually 2 plus H. What does that mean? Well, one way of interpreting that is to say, well, where's 1 plus H? That's the green one. If I take the green coset, and I take any element of the green coset, let's say minus 2, and I add it to any other element of the green coset, let's say 7, I add minus 2 and 7 in the group, the big group, I get 5. I end up in the blue coset, which we call 2 plus h. And it's not necessary that I chose minus 2 and 7. I could also have chosen 1 and 4. If I add those, I get 5, still in the coset 2 plus h. So you take any element in 1 plus h and any element in 1 plus h, you add them, you're going to get in 2 plus h. And it's sort of an easy exercise to convince you that's going to be generally true. So the cosets themselves have a consistent addition, which makes them into a group. Fabulous. So we get this very small group, which is really just Z3, as a quotient of this big infinite group Z by this pretty big infinite subgroup 3Z. This is what we write. We write Z mod H as a set or a type that consists of the 3 cosets. So the elements of this quotient are the 3 cosets. And those 3 cosets have an algebraic structure. They are themselves a commutative group. And we call this a quotient group. So we have a commutative group, G. We have a commutative subgroup, H. Well, any subgroup of a commutative group has to be commutative. Then the quotient G mod H can be thought of as the cosets of H in G. And those cosets can be added by adding representatives. So let's have another look at that concept in the finite situation, see what that looks like. We'll use this group Z12, so all the integers, 0, 1, 2, up to 11. The operation is addition. Addition modulo 12. So for example, 6 plus 7 is 1. Because 6 plus 7 is 13, but 13 mod 12 is the same as 1. Okay, so let's suppose we consider this subgroup H, consisting of all the multiples of 3. 0, 3, 6, 9, well, 12 is the same as 0 again. So that's a closed subgroup of the group, which is, as a group itself, is isomorphic to the cyclic group Z4. So H is a subgroup of Z12. What are the cosets? Well, if we add 1 to each of the elements, we get a coset 1 plus H. That will have elements 1, 4, 7, and 10. Or we could add 2 to each of the elements, so that would be the set 2, 5, 8, and 11. And then those 3 cosets would fill up all of the group. And the quotient, Z12 mod H, is again Z3. In fact, the additive structure here is exactly the same as it was in the previous example. So 1 plus H plus 1 plus H is 2 plus H. 1 plus H plus 2 plus H is H, etc. All right, now let's consider the same big group Z12, but a different subgroup, say the subgroup L, which is all multiples of 4. 0, 4, 8. The next multiple is 12. That gives us back to 0. So 4 has order 3, while 3 had order 4. So this subgroup now is isomorphic to Z3 because it has 3 elements. So this Z3 is now a subgroup of Z12. And what are the cosets of this thing? Well, if we add 1 to it, we get the coset 1 plus L, consisting of the elements 1, 5, and 9. Then there's the coset 2 plus L, which consists of the elements 2, 6, and 10. And 3 plus L, consisting of 3, 7, and 11. And now these 4 cosets together fill out the group. And the addition of these cosets is just like the addition in Z4. So 1 plus L plus 2 plus L is 3 plus L. And 2 plus L plus 3 plus L is 5 plus L, but 5 plus L is really the same as 1 plus L. And here's one more example. If we look at this a little bit bigger subgroup, M, all the multiples of 2, 0, 2, 4, 6, 8, 10. That's a subgroup that's isomorphic to Z6. In this case, there's only 2 cosets. There's the subgroup itself and 1 plus M. 1 plus M would be 1, 3, 5, 7, 9, and 11. And those 2 cosets would fill out the group. And then here's the very simple addition table between these 2 things, and we see that that quotient group is isomorphic to Z2. So a brief introduction to quotient groups. So we've talked about isomorphisms, homomorphisms, cosets, and quotient groups. Next time we'll talk a little bit about free groups, free commutative groups, and then we'll move to the rather much more complicated situation of thinking about non-commutative groups, which are also important in algebraic topology. So let me reassure you, those readers who are not too familiar with this subject, that algebraic topology, at least at the beginning level, which we're at, does not require too much sophistication in terms of our understanding of group theory. We're using it in a relatively simple way. So deeper properties are not going to be too important for us, at least at the beginnings. So I'll see you then.